So today we're going to see how the modern abstract mathematics emerged. And believe it or not, and there is one country which was central to this emergence. And it is somewhat difficult nowadays to talk about this great country because people's minds are closed somewhat to this great place, which was Germany. And we have to understand that by 19th century, Germany emerged as this great cultural power where culture literally became something supreme. Sort of the title of this slide is a quote from sort of concluding aria of Hans Sachs in great Wagner's opera Meistersingers, where he talks about die heilige deutsche Kunst, this holy German art. And people say, oh, no, this is Nazi stuff. No, nothing of the sort. Because what actually Sachs, who is a shoemaker, not a general, is thinking about, he says, when our country is defeated, when there is no government, when there is nothing left, there will remain this great German art. And we have to venerate our masters. So this is not a simple statement. And indeed, Germany created this successive list of masters. In terms of music, again, there were other places which produced composers, but nothing like Germany. Music, as we know right now, and I talk about music as something distinct from Lady Gaga and her ilk. This music which they created was utterly unbelievable. I mean, this list, for anybody who knows music, there are no words, right? They created things of unbelievable, eternal beauty, which will remain forever. In some sense, music and mathematics were closely connected, even from the time of Pythagoras. Remember, Pythagoras viewed music as a mathematical discipline. But interestingly enough, so did Bach. For Bach, of course, it was very clear that music was a solid mathematical discipline. There was great literature, and I put a couple of names you should know, Goethe and Schiller, but there were many, many others. There was great plays by Lessing and Kleist. There were amazing stories by Hoffmann and Novalis. I mean, there was just amazing explosion of creative genius in Germany, except there was no Germany, by the way. There was German countries, oh, so very many of them. And of course, in some sense, Germans invented philosophy in the modern sense, sort of an academic discipline, which is taught now, comes from Germany. And the list is, again, unbelievable, and many great names I had to drop, otherwise the list would be very long. We will talk about Leibniz more, a very great figure, in our third journey, if we live long enough. But Leibniz, Kant, Hegel, Schopenhauer, Marx, Nietzsche, I mean, great names, very different. And in many respects, I want here, when we talk about philosophy, and German philosophy, of course, was known all over the world for its utter darkness and incomprehensibility. Unlike German music, which is absolutely crystally clear and sort of accessible, German philosophy was not easy. It was sort of serious, heavy stuff. Nobody ever picked, the Phenomenology of Spirit by Hegel as a bedside reading. Or maybe one did, but for a different reason. But let me pick Hegel because as a philosopher, he is sort of the central to this group. He is a specifically German philosopher because he was first a great German professor, right? He was so great that one of his younger enemies described his philosophy. It's about absolute spirit becoming the absolute professor, sort of God turning into this ultimate German professor. But while it sounds funny, and is a little bit funny, it's enormous misunderstanding of the importance of this German professor thing. Sort of, they did not just create these wonderful disciplines, they created this culture of professors. And again, let me make a short speech. It's central to, you cannot understand the rest of the story unless you understand that these German professors, especially throughout 19th century, became truly a wonderful species, unlike anyone ever seen before or after. First of all, they were committed to the truth. Sort of, in some sense, they were not there to make money. They were not there to sort of become famous. They wanted to find out what is true. This absolute knowledge, absolute Wissen, the thing which they had to grasp. And they were professionals. They were not, again, far, far away is the world of René Descartes with his sword, who was wandering through Europe, teaching queens early in the morning, whatever. They were professionals. They were waking up early in the morning, shaving, walking to work at the same time, nicely dressed. According to sort of tradition in Königsberg, you could set your watch by Immanuel Kant. Sort of, he would be passing your house on the way to work at 8:06 or whatever, every day without change. Right? For them, their professional status as professor was very important. It was their duty. They were, if you like, high priests of science. Right? But they were also wonderful, wonderful people. They had this collegial spirit, unlike any other group before or since. Time and time again, there would be these stories. One of them would die. Say Minkowski. Some of you might have heard the name. Great German mathematician. Of course, comes from Lithuania. He was Lithuanian Jew. But he was a great German mathematician. He dies. Hilbert, the greatest German mathematician of the time, drops everything he does and starts publishing collected work of his friend Minkowski. That is essential. And it happens times and times again. This is why their work is so well preserved, because when they died, their colleagues would take care of them. There is a great collegial spirit. I encountered a tiny bit of it personally when in 1977, I came to Vienna and was befriended by several old professors. And I was a kid, stupid, ignorant, totally undeserving. They called me kollega, the colleague. They viewed me as somebody who would eventually be their equal. This is, I wasn't, in any sense. And, they were just wonderful. There was something about this German professor which absolutely wonderful. And they took care of their students. That a student was somebody who was like a son. Finally, they would continue each other's research. We shall see that if I die, I would be certain that Tom will finish my work. Well, I'm not now. I mean, it's nothing about Tom. We live in a different world. Sort of, there was a profound responsibility of sort of carrying the torch. And I conclude my introductory speech about great German science with wonderful words from David Hilbert, maybe the sort of the central figure of German mathematics. We'll talk about him in the fourth journey. I moved him. I should have talked about him now. When he was leaving his job as a professor, he gave this wonderful speech, which he said that some people say we will never know the truth. And then he said, we must know, we will know. These are the words engraved on his tomb. One more tomb for you to know. And this is wonderful. It's like getting to the truth is something which we must do at all costs. And of course, these people populated these places called universities. And there was a small town in Germany called Göttingen. And I cannot tell you everything about it, except I could just point at the list of sort of, in terms of mathematics, the list reads like who is who of 19th century mathematics. There are a couple of names missing. Yes, Cauchy was great. He was in France. Yeah, Weierstrass was great. He was in Berlin. But this is pretty much describes 19th century mathematics. Gauss, Riemann, Dirichlet. I mean, this is wonderful list. And I had to drop a bunch of fairly great figures because the list would expand. Of course, they did some physics, like they invented quantum mechanics there. So it wasn't a bad place. This little place won more Nobel Prizes than any other university of the world. As we shall see, it all ends very abruptly. Do you know when it ends? Hitler, 1933. It ends with sort of Minister of Education in Germany issuing a decree that Jews cannot teach. And lots of great mathematicians, such as, say, Courant or Edmund Landau, some of you might know, or Paul Bernays, very great mathematicians, have to leave. Next year, there is a great banquet, German education, and retired Hilbert is invited. And the minister asks him, so after we clean the university, how is mathematics doing in Göttingen? Hilbert looks at him and says, mathematics? There is no mathematics in Göttingen. So again, Hilbert was one of the people who stood up against the Nazis. I mean, again, he couldn't stop them. He was a frail old man, and they were bullies. But nevertheless, I'm proud of them. So let us see how this thing developed, because these are the people who developed abstract mathematics. And in some sense, in order to understand how, remember, our goal is to see how to abstract Euclid's algorithm, GCD. But I have to go in a roundabout way and teach you some stuff before we could do that. So the first person we encounter, and in some sense, the founder of German mathematics in modern sense, of course, there were great Leibniz before, but is this guy, Gauss. And this is a remarkable stamp because it shows us, I cannot tell you everything I know about Gauss because it will take about 20 lectures. But this stamp is a remarkable stamp because it tells you how Gauss became a mathematician. Till he was 18 years old, he didn't know whether he wanted to become a mathematician or classical philologist. He was fluent in Latin and Greek, loved classical literature, and wasn't sure whether he wanted to do this or that. Except when he was 18, he solved one very remarkable problem. Remember Euclidean geometry? It's done with two fundamental tools, ruler at the bottom and compass at the top. And Greeks discovered that they could construct regular triangle, square, and even regular pentagon, which sort of divides the circle in 5 equal parts. They could do hexagon. It's easy if you could do triangle. And then they stop. They don't talk about other regular polygons. Now the question is, could you construct a regular heptagon or so on? And nobody knew the answer till in 1798 or about. Young Gauss, wondering whether he should do this or that, figured out that he could construct a regular 17-gon. That's what you're seeing there. You might not realize. He could divide a circle in 17 equal parts. He actually proves a more remarkable theorem, that for any Fermat prime, do you remember what Fermat primes are? You don't. 2 to the 2 to the n plus 1. If it's a prime, it's called a Fermat prime. So if such a number is prime, you could construct the corresponding p-gon, or 2 to the 2 to the n plus 1 gon, with ruler and compass. 17, of course, is the most interesting case. As a matter of fact, for regular p-gons, that's the requirement. A p-gon is constructible if and only if p is a Fermat prime. 5 happens to be a Fermat prime. So that was a remarkable result. He abandons philology. He still writes beautiful Latin. All his books are written in this just splendid, splendid Latin. Great writer. And starts doing mathematics. So what did he do? Again, I cannot fully describe his life, and he did so much, and all his results are so important that I want just to give quick sort of going through of his accomplishments. By the way, he was known as Prince of Mathematicians, Princeps Mathematicorum. So he was universally recognized as the greatest living mathematician. Not a very easy guy to get along. He had some peculiar habits. For example, he fully believed that if he proved something and didn't publish, priority belonged to him, which is a very strange rule. So, but what did he do? One of his fundamental results very early on is the proof of fundamental theorem of algebra, the first, and actually he gave several, but the first, rigorous proof of the fact that every polygon has a complex root. Any polygon with real coefficients, or even more general, any polygon. Thank you, guys. Every polynomial, polygons, polynomials, it's all the same. Or every polynomial with real coefficient has a complex root, or every sort of extension, every polynomial with complex coefficient has with degree greater or equal to 1. Yes. Constant polynomials like polynomial 5 doesn't have a root. Anil is correct. So that's known as fundamental theorem of algebra. Then we will talk to greater detail. He created number theory. He wrote the first and till today the greatest book on number theory, which is still very deep, very profound, and very few people fully understand what it says. We'll talk about it. Non-Euclidean geometry. And I have to put it in parentheses, because, of course, he very early on realized that Euclidean fifth postulate, a reminder, that if you have a line and a point outside the line on the plane, there's only one parallel line through this point, parallel to the original line. And you say, well, it's self-evident. Well, it's self-evident, but people tried to prove it and couldn't. So Gauss suspected that you actually could have and consistent non-Euclidean geometry, where you could have multiple parallel lines through a point. We know that he discovered it because he made notes in his diary, and we have his diary. So he doesn't lie. Then, of course, much later on, a great Russian mathematician, Nikolai Lobachevsky, publishes a book where he develops this geometry with all its sort of unbelievable consequences, very different from normal geometry. And Gauss, by the way, is so interested that he learns Russian in order to read Lobachevsky's work. Not a simple thing to do. But he's a very able linguist, so he could just pick languages easily. Then his friend, he had a Hungarian friend who sends him a book by his son, János Bolyai, a Hungarian kid who developed independently from Lobachevsky, not as deep, and a little bit later, the same sort of results, and the book is published. He is clearly independent and wonderful results. So Gauss answers, well, I have done it all a long time ago. The kid is devastated and eventually loses his mind, literally. So very sad story. So Gauss was not always sensitive and clearly didn't realize that the fact that he thought of something does not constitute priority. You have to publish. He was very careful with publishing. That is one of the sort of the greatest mathematician before him. Euler published unbelievable amount. Gauss was very careful. He would publish only these perfect gems and work on every paper till it becomes sort of unparalleled. So he had another thing, which I need to allude because we're going to encounter it. Sort of Euler, when he presents a result, would be very careful to explain to you how he got the result. Gauss was the first mathematician who established this wonderful tradition that you should give the shortest possible proof and hide all the traces of how you actually got the result. Some of you who studied mathematics know that that's how mathematics is done now. And some of you might say, Alex, look at the mirror. Guys, I'm just a product of a certain system, which went back to Gauss, hiding the results. I'm trying very hard not to do it, but nevertheless. So he would hide the way. You could never figure out how he got this beautiful result. He proves it beautifully, but it comes from heaven. It's sort of, you absolutely could never guess it yourself, nor will you ever figure out the proof. So he basically invents modern statistics. He does remarkable work on celestial mechanics. When there is a survey going on, he volunteers to help, and while just observing sort of land measurements, invents the notion of curvature and founds the field of differential geometry, just in passing. When he is fairly old, a young scientist comes to the university by the name of Weber and starts playing with electricity. So Gauss joins, does some fundamental work on electromagnetism, and invents the telegraph, just to show you the scope. The guy is utterly amazing. But the book with which we're mostly concerned, the number theory books on which sort of all the modern number theory is based. This is the first text. It's like Euclid for geometry. This book is for number theory. It's called Disquisitiones Arithmeticae, and it means investigations in arithmetic. Arithmetic for him, the science of numbers, number theory. It doesn't mean it's about 2 plus 2. It's a very, very complicated book. That's the outline. First of all, he starts with the first rigorous proof of the fundamental theorem of arithmetic. Reminder, it means that every integer has a unique decomposition into primes, right? Sort of, obviously, Euclid could have proved it, but didn't have a notation. It's a long discussion, but sort of. Then he invents modular arithmetic. You know, when you do this mod this, Gauss. He just introduced the notation, does it all. Then bunch of things we don't need to talk about, and just to complete construction of regular polygons. All right? He builds this theory of regular polygons. It's a remarkable book. I didn't bring it, but I have it in my office. And it is quite wonderful. It is very difficult. Sort of after about 100 pages, you have to be really, really good to understand what is he really doing. It's written beautifully. But you understand every word, you understand every sentence, but then you read and say, I don't know what he's talking about. It's difficult. His goal was not to make it easy for you, but to write a beautiful book. He succeeded. So as we shall see, it required several generations of interpreters to be fully understood. So, and now we go back to Gauss's remarkable algorithm for finding greatest common divisor. Remarkable in quotes, because our friend Gauss is very, very proud. He just proved this fundamental theorem of arithmetic, yes? So he tells you how to find greatest common divisor. He says, you take two numbers, you decompose first one into primes, then the second one into primes. Then you get the common primes from both and multiply them together. And that's how you get greatest common divisor. You see, it's actually awful. Because what he told us, that instead of doing something very simple, we have to do something very, very hard, technically hard, exponential. Because breaking a number in prime factors is very hard. But Gauss was so great that from that point on, basically, all the elementary textbooks in Germany, Russia, eventually United States, drop Euclid's algorithm completely. This is why you didn't learn it in the 5th grade. And that's why they teach Gauss's algorithm, because couldn't argue, he is so great. And of course, he's not stupid. And look what he says. And this is the last sentence of this corresponding section. When it's very hard, we know some elementary way of doing it. But he doesn't tell us what's the way. So he is so against Euclid's algorithm that in the entire book, he doesn't mention it once. He alludes to it, saying that when we cannot do mine, which basically in any interesting case you cannot do, there is some other unnamed one. Right? No description, no reference, no name, nothing. So, by the way, typical Gauss. This is, for me, this is Gauss. Only he could do that. And, but fortunately for us, he was not consistent. That is, if he needs something for his work, he was able to finish this book without ever using Euclid's algorithm. But eventually, he had to encounter it. It took about 30 years. Now, for 30 years, as far as I know, he never once mentions Euclid's algorithm. He teaches number theory. He is the first person who started teaching number theory. He teaches a course, doesn't mention this unknown elementary method. Just doesn't mention. But then, he does another remarkable discovery. Remember, Stevin invented real numbers. But real numbers, in some sense, are not complete. What means not complete? There are some polynomials which do not have roots, which are not solvable over reals. I mean, the simplest example is x squared plus 1 equals 0. Just cannot solve it. Of course, people knew how to solve it. Even in 16th century, Italian algebraists, particularly Bombelli, I guess, introduced I, this imaginary number. And Euler uses this imaginary number everywhere. But it's an imaginary number. It's not real number. It's a figment of our imagination. So people feel quite uncomfortable with it. And Gauss, for the first, say, 30 years of doing mathematics, uses, we know it for a fact, he would use complex numbers in his proofs, in his diary, but then will reconstruct the proof so to get rid of any mention of this imaginary I thing. In several of his letters, he writes the metaphysics. Don't forget, he's a German professor. So he writes, the metaphysics of I is very complicated. It's not clear what it is, so he doesn't want to use it. He would use it to get an answer, but then he will hide the traces. Well, he would never do that. So, and then suddenly he has this unbelievable insight. It's very clear. I mean, people argue who had it, and there are some people who had it a little bit before Gauss, but the person who brings it into mathematics as a full-fledged, real thing, I mean, complex thing, is Gauss. He invents the term complex numbers, because prior to that, there are real numbers, and there is this imaginary I. Gauss says, no, they are complex numbers. It's a pair A plus BI. And it has very natural interpretation. It's not a figment. If I take a Cartesian plane and I position I as a vector orthogonal to my real line, everything makes sense. That was a remarkable discovery, and that makes complex numbers the central part of modern mathematics. You could not sort of live without them. And, by the way, he also invents a very important subset of complex numbers, which he calls complex integers, because he couldn't quite call him Gaussian integers the way we call them, but that's what they're called. So if you take complex plane and you would take integer grid, all the complex numbers with integer coordinates, these are called Gaussian integers. And if you bring them into sort of number theory, lots of very complicated proofs become very simple. It's a remarkable, remarkable tool which Gauss discovers. By the way, quick reminder, complex numbers. So complex number has a conjugate. So if number is like that, conjugate is like that. If number is like that, conjugate is like that. Right? You flip the imaginary part. Real part is x, imaginary part, norm or complex norm, and there are multiple people who say what norm is. Some people call absolute value norm, but I stick to Hardy and Wright terminology, calling this norm. Absolute value, how long the complex number is. Argument, which is the angle. Right? That's how you do addition, subtraction, multiplication, and reciprocal. If you could do reciprocal, you could do division as well. A simple test problem, just let us, after we know all of that, I gave you some reminder. If we have a complex number I, what's its square root? Anybody? What's the square root of I? Not square root of -1. What is the square root of I? Okay. If you don't remember, let me give you a few hints. What's the absolute value of the square root? 1. It's not going to change. What's the argument of square root? 45 degrees. Do we need to continue, guys? No, we don't need to continue. You could go back, plug it, and get the numbers. So remember, when you multiply two complex numbers, you add the arguments, you multiply the absolute values. A very simple rule. Right? So just a reminder. Now we will have to do a little bit sort of Gaussian integers. These are the things. And let me show you quickly that what you could do with these integers. You couldn't do full division like with integers, but there is division with remainder. And Gaussian integers have a very, very nice remainder. So how do you do it? You basically want to divide two numbers. What you do, you are dividing z1 over there, do you see up there, by z2. So you construct a grid based on z2. z2 minus z2, I z2, all these things. You construct a square grid, right? Now, it's obvious that z1 is going to be inside of one of the squares of the grid. And the remainder, because any of these numbers in the grid is a product of z2 times some other complex integer. So that will be a remainder, so you just subtract it. This is good enough. We could write an algorithm, but we don't really need to do that, because what is so wonderful is that Gauss discovers that if he uses this remainder, Gaussian integers could be used with Euclid algorithm. Euclid algorithm comes back in exactly the same, the old form. Nothing changed. Just the type changed. Right? And why is it so wonderful? Because somehow you could prove enormous amount of results from the existence of this algorithm. For example, you could prove fundamental theorem of Gaussian integers. What's the fundamental theorem of Gaussian integers? Unique decompositions into Gaussian primes. That is, that Gaussian integers, in some sense, are similar to normal integers, and the same algorithms are used. They're a little bit funny, because not everything you know about integers remains for Gaussian integers. For example, 2 is not a prime. Why? Because you see, 1 plus I times 1 minus I is equal to 2. Right? So 2 is not a prime. They're different. But there are deep connections between primes, Gaussian primes, and simple primes, and whatever, traditional primes. So, which allows us to do many, many things. So here I have to cover lots of stuff. Gauss dies, and this guy try to pronounce all of that. People call him Peter Lejeune Dirichlet. He is German in spite of French name. As German as they come. He had a great-grandfather, well, he had a grandfather who was born in Belgium. But he was German, grew up in Germany, sort of was a great German patriot, was married to a sister of Felix Mendelssohn, great German composer. So was quite musical, very democratic during the revolution in 1948, joined the Guard and was issued a rifle and sort of wanted to defend liberty against, the aristocrats. As far as I know, never fired a shot, but guarded some warehouse or something, which is a good thing. Several facts of his biography, which is important. When he was very young, he was able to come up with a proof, somewhat incomplete, but a proof which was accepted, of Fermat theorem for n equal 5, which was a big deal. Because Fermat proved last Fermat theorem for 4. Remember last Fermat theorem? A to the n plus b to the n is equal c to the n. You cannot have solutions. So Fermat proved it for 4. Euler proved it for 3. Dirichlet starts it while still an undergraduate, proves it for 5. Big deal. Becomes accepted among the mathematicians as a brilliant guy. And then he buys this book by Gauss and realizes that it's very difficult. So according to legend, I wasn't there, he sleeps with the book under his pillow for years. He sort of reads it till time and time again. till he fully masters it. And sort of indeed masters it completely. I could prove that. I'll prove it in a second. His complete mastery, because you will see. And then eventually, when Gauss dies, succeeds him as to the chair of mathematics in Göttingen. Again, a wonderful guy, by the way, kind to other mathematicians, would just do unbelievable things. Nobody nowadays would even think like, would drop his work, go travel with a sick friend, you know, just do all kind of remarkable things. Wonderful, wonderful person. So sadly enough, dies young, gets a chair, in about 3 years he's dead. That's how it goes. But his greatest result in number theory, where he sort of succeeds Gauss as the number one number theorist in the world, is a remarkable result I mentioned before about primes in arithmetic progression. If you take a progression, if you take, say, numbers of the kind 4, okay, let me pick something, 7n plus 5. Numbers which give you remainder 5 when divided by 7. It's arithmetic progression, right? Are there any primes? Well, he says, yes, infinitely many. In any arithmetic progression, there are infinitely many primes. As long as the base, 5 and 7 are coprime. For example, 4n plus 2, no primes. Oh, well, obviously, I'm sure you could prove that. Right? So, and what the reason I want to talk about him in this thing is multiple. He deserves to be talked about. But this is a quote from his great lectures of number theory. You see, he sleeps with Gauss's work under his pillow, absorbs all it, try it, and comes up with the second great text. And in some sense, greater than Gauss, in some sense. Gauss is still the first and greatest. But this is an amazing book, and now translated into English by a wonderful person by the name of John Stilwell. So I had to quote something from his lectures. What he says is the whole structure of number theory rests on a single foundation: the algorithm for finding GCD of two numbers. That is, he says that this Euclid algorithm is not just an aberration. It's not just everything we know about numbers is based on this algorithm. And it takes a long time to fully explain. I'll give you a glimpse of it. But the fact that somebody as great as Dirichlet says that, remember, by the way, Gauss never mentions it. So the second book puts it at the center of the edifice. All subsequent theorems as just consequences of investigation of this algorithm. And what does he, another quote from him. This is also from Dirichlet. Let us take numbers. Remember, Gauss introduced numbers. I kept not AB but Tn, this bizarre thing, but that's what Dirichlet uses. I couldn't, some mathematicians are just mad. Why would you use T and N instead of A and B, and putting N instead of A, which any sensible person would do? But, that's how he does it, so I have to. So, of course, Gaussian integers, A is just 1. But what Dirichlet realizes, that you could start plugging many other integers there, and you get other kind of theories, more and more complicated, more and more interesting. Okay? Of course, we will see in a second why he is doing it. And then the hope is that for all these integers, GCD will work. Sadly enough, and you will know in a second why it's sadly, it is not going to work, for example, for -5 there. Because if Euclid algorithm works, you get unique factorization. And for -5, there is no unique factorization, because 21 could be decomposed into numbers of that kind in 2 different ways. And you say, so why would anybody care? It's a very good question. I mean, normal person wouldn't care. The slide is lost. OK, I could tell you without the slide. Because you see what they realized at that point. Where could... OK. Let me just... The slide is there. I moved it. So you will know in 5 minutes. So just wait 5 minutes why it matters. We come to another guy, Richard Dedekind, another wonderful guy, student, in some sense, not formally speaking student, but a young colleague of Dirichlet. He joins the faculty as Privatdozent, assistant professor at Göttingen, and starts attending lectures by Dirichlet and gets very excited, writes it carefully, and when Dirichlet dies, he writes a book. The book which we know is Dirichlet Notes on Number Theory. It's actually not written by Dirichlet. It's written by Dedekind and published without mentioning himself. More importantly, then for many years, every few years, he publishes new edition. Dirichlet is perfectly dead, right? So he puts more and more results, new and newer results, some of which are not Dirichlet results, are his results, put them as appendices, more and more appendices, publishes new edition, never mentioning himself. Remember I was talking about this collegial attitude. You know, he had an older friend who died. He's continuing his work. He doesn't need to be mentioned. Right? So the greatest book Dirichlet wrote, he never wrote. But it was written by Dedekind, and we will talk about Dedekind quite a lot during the 4th journey. But he's central to our story here too. Also a wonderful guy, sort of a very humble guy. Sort of, he could never push himself. He sort of will give away his results, suggest to other people, encourage other people to succeed. Therefore, never gets tenure at Göttingen. Eventually has to go teach at, by the way, his advisor was Gauss, so it's a nice connection. He eventually has to go and teach a technical university in Braunschweig. And I cannot explain to you the difference between Göttingen, a technical university, and Braunschweig, which just became technical university just then. Before it was like school for talented working class kids. It wasn't a university. So, but he goes there, and he was from Braunschweig, so he happily lived there, sort of taught students whatever they needed to be taught, lived with his sister, never married, very sort of quiet guy, very great mathematician. So what he invents, ring theory, we'll see it's central to abstract algebra, the notion of algebraic integers, and comes with, you know, some of you might have heard of Dedekind cuts, the foundation of modern real numbers. But more importantly, he's the first person to construct what's considered modern rigorous theory of both integers and rational numbers, other than just real. A very great mathematician. So, but very unassuming, lives very long life, never gets drunk, and disorderly, sort of nothing exciting. Wonderful guy. So what he understands now, that there is a general pattern there. There are integers, there are Gaussian integers, there are few examples from these other quadratic extensions which Dirichlet mentions, you know, square root of -5. So he comes with a notion of algebraic integers, which are roots of monic polynomial. Monic polynomial is a polynomial with coefficient 1 here, right? These are examples of monic polynomials. And so x squared plus 1 generate Gaussian integers. X cubed minus 1 generates Eisenstein integers. Very, very nice sort of kind of integers. x squared plus 5 generates this quadratic, imaginary quadratic ring of square root of minus 5. But there are lots of them. And why everybody is excited is that a French mathematician, Lemay, while these guys are doing this stuff, and everybody, by the way, every respectable mathematician claims that he doesn't care to prove last Fermat theorem. And somebody asked Gauss whether he is interested in the proof of last Fermat theorem. He says, I don't do trifles. Of course, he lies, because we have his diary. He does do trifles all the time. He wants to prove it, but he cannot. So nobody would acknowledge. By that time, it becomes totally not right to say you're interested in that. You're supposed to ignore it, sort of. Because you couldn't, especially if you're Gauss, you could say, I'm working on it, but I could solve it. Because you're the prince of mathematicians. So, but everybody knows that there is this guy, Lemay, Frenchman, who figured out the following thing, that if, let me simplify it dramatically, that if for these algebraic integers, which Dedekind invented, but more specifically of one kind of integers, integers like Eisenstein integers, they're known as cyclotomic integers, integers which generated by nth root of 1 on complex plane. Cyclotomic means circle dividing integers. Then we could prove if Euclid algorithm works for these integers, we could prove last Fermat theorem. Right? So more specifically, if there is unique factorization for these integers, we could. So everybody wants to do something. They're trying to say, well, maybe not them, maybe could extend them. Enormous amount of work. And the entire foundation of modern abstract algebra is these secret attempts to come up with the proof of last Fermat theorem by finding the right kind of integers where this sort of unique factorization would work and things will happen. By the way, this attempt fails, but it leads to remarkable results. Well, see you in 7 minutes.